Awesome, thank you. So it's a pleasure to have Hoi-To Wai presenting today their seminar. Hoi-To is an assistant professor at CUHK in Hong Kong. So he's dialing in from there. And he graduated from CUHK, both with bachelor's and master's. And he got a PhD degree from Arizona State University in 2017. And he also had some research positions at MIT and Telecom Paritech. And I think that this work especially came out of that collaboration with people there, and also at UC Davis, and received a bunch of awards like the Dean's Dissertation Award, ASU, and the Best Student Paper Award at IEEE ICASP in 2018. And he's also well known for running another virtual seminar series. His current interests are networking and communication, and that's what that seminar series is about, I think. So with that, Hoi-To, the stage is yours.
Thanks, Chaba, for the very kind introductions, and I also like to extend my thanks to everyone who wakes up early for this talk. I know it's 2 hours earlier than usual, so thanks for staying up with me. I mean, waking up because of me. So I hope that you served yourself with coffee and so to keep yourself awake. So okay, so let me begin my talk today. So I'm going to talk to you about some recent results about linear two-timescale stochastic approximation algorithms. So precisely, I'm going to present a new, actually like a refined analysis that works with the cases which we are quite interested in nowadays, where, for instance, when we have Markovian noises. So just as Chava said, this is a joint work with a few of my collaborators, especially Eric Moulines, who is from France. This is also a joint work with a few other guys from Moscow. So Alexey and Maxim, and also with Tadic from Bristol. So the paper is actually available at the code this year, and you can actually download this from the link here. So this is what. This is what I'm planning to talk about today. So first, I'll actually go through a really gentle motivations and examples of why are we interested in a two-timescale stochastic approximation algorithms. Then this will be the motivations, and then I will actually talk about some I will actually describe the setup in greater details and more formally, and also point out what are the challenges in the analysis ahead. Then in the third session, this will be basically the main parts of this talk, where I will discuss the main results and trying to present with you some proof sketch. And furthermore, we also show an asymptotic expansions that actually shows that our bound are sort of optimal. And finally, there will be a summary. So, okay, and before I begin, I would also like to invite everyone to stop me if you find anything confusing or so. I mean, feel free to do so. Okay, so let me first have a one-slide introductions of why are we interested in stochastic approximations. So as we know nowadays, actually many reinforcement learning problems can be boiled down to that of finding just a fixed point to a certain nonlinear map, nonlinear equations. So one of the famous examples is that, for example, you want to find a fixed point to the Bellman equation. And that is the question that you ask when you want to do policy evaluations for a certain policy. So most of the time, the question is just to find a certain point called theta star, such that when you evaluate the map f of theta star, and the map evaluates to 0. So that is the question or the problem that you're willing to solve. And in the RL settings, in most cases, you only got to observe some stochastic samples of this function. So it is not as easy as you can always evaluate it. You don't have it in most of the time. So therefore, and in those cases, since you only have stochastic samples, you have to apply some iterative steps to help you in finding the solutions. And one of the famous examples is the so-called stochastic approximation scheme, which is now 70 years old by now, created by Moulines and Monroe. So the idea is simple. So you have some random samples, and then you iterate through the update. So you have the stochastic samples, and then you move your points accordingly with the different step sizes. So here you may notice that there's a thing called xk plus 1 here. So this can be thought of as a random seed, which governs how this stochastic sample is like. So in the RL settings, sometimes you may want to run your algorithm by running through a single trajectories of Markov chain. And in those cases, you will find you find yourself in a situation that the expected value of the stochastic update is not exactly equals to the fixed point equation you want to evaluate. But since this is Markov chain, it may have a stationary distributions, and so that as k goes to infinity, you can find it. So then the question is always like, do you want to wait until that long until you can find an unbiased estimate of the update rule? So it turns out that you don't have to wait until that long, and you can simply run the iterations just like this. And this is actually the topics for many old and new works for understanding the performance of this SA, or so-called stochastic approximation scheme. So this is what we know so far about the standard stochastic approximation schemes. So what can we do next? What can we do further? Let's say now we want to. So I actually saw a question about what is the capital F here. So the capital F here is actually like a stochastic version of the original function f. So you may think of it as so this is a function that can be evaluated from xk plus 1 and theta k. So this can be regarded as a noisy version of function f of x theta k.
By the way, are you going to have some example later for this capital F?
Yeah. Yes.
So maybe that will make it very clear what this capital F is, right?
Yes, precisely.
Yeah, this expression was pretty good. Yeah.
All right, cool. So so here in this talk, we are not going to we're going to look at a slightly more complicated problem. So precisely instead of solving one equation, let's try to solve two simultaneously. So we have two equations. So when the goal for this talk is that we want to find a fixed point theta and w such that it solves simultaneously f1 and f2. So this is actually a problem that can be found in many settings, especially from optimizations. So for instance, if you have if you want to solve a saddle point problem, so that means you want to find the mean mass solution of a function that's called L, theta, and W. Then you can actually set f1 to be the gradient with respect to theta, and then f2 to be the gradient with respect to W. And then you have and then you can recast the saddle point into a fixed point to this guy, into the fixed point conditions. You can also cast a bilevel optimization problem into the similar model with a more complicated form of the f1 and f2, so which I'm not going to discuss too much here because this remains a little bit abstract here. So well, just like what I did in the first slide, the first slide. So here we only get stochastic samples, and also the system is being a coupled system. So So once again, I suppose that xk plus 1 is now the random seed I observe at iteration k, and then f1, f2 are like the corresponding stochastic version of f1 and f2 respectively. So let's try to explore what are the ways we can use to solve the system of equations. What will be the ways for doing so? So remember that the system is coupled together. You have to solve f1 and f2 simultaneously. So now suppose that theta is a fixed quantity. So now you consider and update rules of this form. So which is nothing too much more complicated than the stochastic approximation scheme I did at the beginning. So because I'm not going to modify this theta at all. So then now using the existing theory you knew about stochastic approximation, by running this iteration, you're going to find a point called W star theta, such that F2 theta and W star theta is going to be 0. So this is a fixed point to F2, given that theta is fixed for you. So now that you notice that you have a way to evaluate this thing called theta's W star theta. Now you can go one step further. So you now go back to F1. And then F1, you're going to do the following updates. You're going to take out the stochastic samples of F1 and then evaluate it at theta k and W star theta k. And once again, this is like a one equation stochastic approximations. Running this until infinity, you're going to find a point called theta star, such that theta star W star theta star is going to be 0. And then in this way, by running the two recursions in this format, you're going to solve the fixed point equations, and then you're done. So, but then in terms of the real implementations, you're going to do you will have to do the following, because remember that you want to find the W star theta first in order to run the second equations. So one way to do so is that you when you write your program, you create an inner loop iterations that updates the WK. And then after a sufficiently large number of iterations, you do one step of the theta update. And then eventually, you're going to solve the fixed point equations. So this is a double loop algorithms, which is kind of reasonable, given that we knew how the previous how the original SA algorithm is going to work. But this is not ideal because it involves programming a double loop algorithms, and you want to do something cleverer than this. And so luckily, it was proposed in 1997 by Bocker that you can actually do the same thing. You can find the solution in actually a single loop algorithm. The way to do so is that you're going to run the two. You're going to update your theta and W the same way you would imagine to do, as if you're running a standard stochastic approximation. But then you're going to play a trick with the step sizes. So here I call the step size with the theta by beta k. I call the step size with the W by gamma k. So this is important, and we're going to require the following conditions. So this condition says that beta k divided by gamma k is going to tend to 0 as k goes to infinity. So what that means? So it means that beta k is going to be much smaller than gamma k when k is sufficiently large. So what that means, so now you go back to the equations. So since beta k is very small, so imagine that you're now trying to update W. So with respect to W, the theta k is almost like a static item to me when I try to update my W. And then since this is almost static to me, so if I want sufficiently large number of WK updates, I'm going to find something like W star theta k here. It will be tracking this quantity very closely if I'm wanting this update under this rule. So that is actually the very cute idea of the two-timescale stochastic approximations, where you're trying to track this update using two different timescales in your algorithm. So, but of course, this is a relatively old thing because it's from 1997. But so here in this talk, we're going to present an analysis on the two-timescale schemes, where this xk is Markovians, but we're going to focus on a special case where the stochastic updates, this capital F1 and F2, are simply linear functions of theta and W. And I'm going to present an example why this is important to us. And it is actually an example that I believe many of us have heard about, and that is the policy evaluation problems, the old school one. So I guess I can mostly skip the discussions here. So this is so we consider discrete finite state space state action space model with a stationary policies, and we're going to find and our goal is actually to evaluate the value function for a discounted reward where the discount is alpha. So this is the value function we want to find, but knowing that this value function is defined on the state space, and the state space can be large. So we're going to use a function approximation approach to find a lower dimensional representations of V pi. So we want to find a linear function parameterized by theta, such that the value it approximates the V pi. And so here the linear function approximations is defined by using the feature map, which is predefined, and we call it phi s. And one way to actually if we want to cast this problem as an optimization problem, so one way to find the best theta, the best approximation, is try to minimize the following objective. That is called the norm of the expected TD update. So this update is defined as the norms as the Euclidean norm square of the expectations of the feature map multiplied to the TD error. So this is the objective functions that we want to minimize. So of course, the first thing we want to do is that let's try to compute the gradients of this NEU function. So simple linear algebra tells you that you can evaluate this. You can evaluate these gradients of the gradient of this NEU function by this guy, Noise function, and so then you see actually this is computed by the multiplications of two expectations. So you may want to use a naive estimator by taking the state at k and state at k plus 1 and state as k, and then you multiply everything together. It does not work because if you try to take an expectation of this, it does not give you the gradient of theta. So that is not a nice idea. So that's why back in 2009, Sutton et al. Proposed a solution called the GTD0 algorithm, which actually tried to extend this fixed point equation. It tries to extend this fixed point equation by splitting them into two. So one that involves a new slack variable called W. So trying to find something that is taken from here, multiplied to your W, and then trying to make sure that this W will also be equals to this guy. So, so now that you have two equations, and I can formulate a linear TTSA scheme by merely taking stochastic samples from these expectations. So that means I'm going to take the state at the kth time step minus the discount factor multiplied by the step at k+1 steps, and yada yada. And I mean, you work out the details, and you find out that you can have a linear TTSA scheme. So once again, we have the step size by beta k and gamma k, and you will see that this is actually a linear update, because here this whole thing doesn't depend on the, wk nor theta k, and this is a linear map of w, and then this is again a linear map of theta, and this is a linear map of wk. So this is a linear formulations of the TTSA, and this is one type of the optimization of the TTSA scheme that we want to analyze in this paper. So is there any problem with the motivation so far? So I think I saw a question saying that whether this objective coincides with the least square objective, and it is actually a least square objective in this way. And actually, you can further rewrite this objective into something like a theta minus b square, and you can find out the corresponding a and b in this case. So this indeed corresponds to a least square objective. Okay, so let me move on to the more general settings, to the more formal discussions of the analysis. So the previous slide only tells you one example of linear TTSA. So in the most generic form, we're going to have the theta update to be governed by having one matrix multiplied to theta k, another matrix multiplied to w. So we're just going to call them with some boring name with A11, A12, and yada yada, and B1, B2. So here we can define the so-called mean field matrices by taking the expectations when k goes to infinity. And we're going to use bi and aij without the tilde to denote them. And also this A11 aij tilde are correspondingly random functions that has matrix or vector valued. And it is measurable with respect to xk+1. So once you give me the state, once you give me the state xk, this thing will be deterministic. But then xk itself is not is actually random. So then, of course, based on the mean field, you can define what is the fixed point. But this is just linear algebra. So our result does the following thing. So our first goal is that we want to analyze a finite time error band in terms of mean square error, characterizing how close my theta k is away from theta star and wk is away from w star. We're actually going to look at two different settings regarding how this xk is going to behave. So number one is that the A setting is that when it is simply like IID sequences, IID samples, and B, which is the more challenging, the more exciting settings, where this xk forms an ergodic Markov chain. Okay, so actually we can reformulate the previous equations in a different way. So one way is actually, to so what I want to do in this slide is that I want to do some recentering to make the analysis a little bit nicer to look. So I can define this wk and vk as the so-called noise vector. So I'm going to take out those A11, A12, A22, A21 without the tilde. And then I'm going to put everything that is not going alongside with the mean field matrices into this VK here. So once again, this simple algebra. So I just do some add and subtract, and then you can find out the relationships here. So what is important is that imagine that now if xk are just a bunch of IID samples, and then now you try to evaluate the conditional expectation of Vk or Wk plus 1. This is going to be 0 because if I condition, since this is IID samples, the expectations of B1 tilde will be equals to B1. And since I'm taking conditional expectations up to the kth iteration, this thing will be sort of deterministic to me, and then this thing has a 0 mean. So this is, and in this case, we can also say that this Vk plus 1 and Wk plus 1 are martingale noises. And of course, in the other cases where xk forms an ergodic Markov chain, this the conditional mean will no longer be 0, and this is why the Markovian noise cases are challenging to analyze. So let me describe a few prior works that are relevant to this paper. So given that this is a challenging problem and has a number of applications, so actually some earlier works has done a lot of things already. So for instance, the first paper from Bocker actually proved the almost sure convergence, assuming that you have bounded iterates. And then there's a landmark paper by Condon-Tsitsiklis in 2004, which proved the steady state weights of convergence by assuming that the noise are martingale. And on top of that, they assume that the variance is uniformly bounded. But the results they proved is very interesting. So they showed that actually theta k minus theta star, so the optimality gap for theta is going to have a steady state error of beta k. But on the other hand, if you look at the optimality gap for wk, it's only going to decay at gamma k only. So remember that we have these conditions of gamma k, beta k goes to 0. So it means that by looking at this result, you see that your theta actually goes to 0 at a faster rate than the others. So that is an interesting observations that they made, and because basically the observations is reasonable in the sense that since you're using the step size of beta k to update your theta, it is supposed to converge at that rate as well. And you can see that there's a difference in scales of the convergence. And then recently, actually in the last 2 or 3 years, I noticed that there are a bunch of work popping up trying to provide finite time bounds on the linear TTSA algorithm. So a few of the more representative works are as follows. So in Delau et al. In 2019 shows that actually this, in the case of martingale noise, you can show the same steady state weight as equation 1. So that is kind of the best result available now. But then in the Markovian noise settings, where, as I said, the xk's are drawn from Markov chain, in those cases, people didn't find the same weight as before. So they found that, so for example, Su et al. And Doan show the MSE bound, which is to say that theta k minus theta star has the weight of gamma k. So that is actually the worst weight we saw in the we have in the TTSA scheme. So, and of course there are many others. So if we want to zoom out, So this is the current state of the art for the analysis for the finite time bands for TTSA. So we notice that for IID noise, that is very nice because we have the separation of times of step sizes. And then for Markovian noise, it is not quite nice. So this work is simply to close the gap. So we're going to show that even in the case of Markovian noise, everything that you expect from the condenser cyclist work still applies to the Markovian noise settings. And also some highlights of our analysis. So we present a finite time analysis that is refined, doesn't require boundedness assumptions. So we are looking at so what I mean is that we are looking at the most original linear TTSA scheme that doesn't attempt to bound the iterates into a bounded set. And also we have improved the finite time bands.
Yeah, just to clarify, the difficulty there is that in these linear updates, you're multiplying the vectors, and part of the noise is coming dependent on the magnitude of the parameters you're trying to estimate. And so if those parameters would grow unbounded, then your noise is going to grow unbounded, and you're running the risk of blowing up everything. And so that's why it's challenging.
Yes. So the answer is yes. In the noise time is going to increase according to how large your parameters are, and we are going to show that even under this assumption, the noise eventually the algorithm is going to converge. So actually what you mentioned is actually one of the problems where the Lau et al. Tried to fix over the condenser cyclist paper. So because so in the condenser cyclist paper, so one of the assumptions they made is that those VK and WK has a finite variance. So which clearly doesn't apply in the most general TTSA linear TTSA settings. And then in the Lau et al, they actually show that even if the noise is actually growing up with how large your theta and WKs are, it's still going to converge. But they only focus on the martingale cascade settings. So is there any questions about the highlights of the contributions?
I think that there was just a note in from Tinduan that he said that there is no projection in their work.
Yeah, I remember. Yes, okay. I think Don doesn't do the projection, and Sue did the projection. That was the difference. So yeah, so my mistake. Sorry. Okay. So let me present to you some summarizations of the main results. So of course we're gonna need some assumptions. So these assumptions are rather standard here. So we're gonna assume that the system matrix is a Hurwitz, which basically guarantees the linear TTSA systems in the mean field are stable. We're gonna also assume something about the step sizes. So here we are. So you see a lot of equations here. So let me just give you an example. So one of the examples is that we can set beta k to be in the order of 1 over k for beta. We can also set gamma in the order of 1 over k 2 over 3. So which is a popular choice in the literature, and you can verify that this satisfies the assumptions. And moreover, these assumptions also hold for even if you want to use a constant step size, piecewise diminishing step size, they all hold in the current settings. So furthermore, since we're going to present first the result when we only have martingale noise, so technically these are the assumptions we need. So we need that VK and WK are conditionally zero mean. So which can be done if your XK are drawn in an IID fashion. And furthermore, the second order moment is going to be bounded in this way, such that it grows with theta k as well and wk. So I guess that is that also answers the previous question. So under these settings, let me present the first result here. So this result doesn't require the projections and also shows the separation of scales. So what it says, so it says that if I want the MSE for theta is going to be bounded by the composition of two different terms. So modulo a lot of constants. So the first term here is what I call the transient term. So basically, you can see that it is a multiplications of many numbers that are smaller than 1. And it actually depends on the initializations, like how close you are to the initial optimality gap. And so this is the transient term, which decays basically exponentially or subgeometrical, or exponentially in most of the case. And then there's a steady state term that is actually proportional to the step size beta k here. So this is what we show for the theta k. And also we can show this for the wk, which is in the order of gamma k. So once again, this is an improvement over the Dallaire et al. In 2019. So here where we analyze really like a plain linear TTSA without the projection. So that is the martingale case, but the more interesting one is the Markovian noise case. So in the Markovian noise case, we don't have the zero mean for the assumptions for the noise anymore. So we're still going to assume something about how those xk are generated. So here you go. So what we have is that we're going to assume that the Markov kernel is irreducible, aperiodic, and it has a unique stationary distribution. Also, we're going to assume that those functions bi and aij's are uniformly bounded. So meaning that no matter what x you plug in, you're going to have a bounded functions in all cases. So these are sort of standard assumptions nowadays used in modeling this Markovian noise. And what is the important implications about the assumption A5 here is that it implies that the following equation, let me try to highlight this here. So this equation does have a solution. So what does that solution means? That solution means that we have a function called bi hat, such that if you calculate basically the noise, the bi tilde and bi, it's going to be equal to bi hat evaluated at x, and also the Markov kernel applied on bi hat x. So, and precisely you can evaluate this bi hat and aij hat by evaluating like an infinite sum, and that is actually the reason why we have to assume that it is an irreducible Markov chain, because we want to make sure that this equation is well defined. It doesn't blow up. So this is the conditions we're gonna use in our analysis, and the main message is that having this so-called Poisson equation is going to allow us to decompose the noise terms into a martingale components that is easy to analyze, and also the so-called finite difference component that is going to be small if we move on to the analysis. So this is the assumptions we need for the Markovian case. And we also need further restrictions on the step size, and which is actually not too restrictive. The only thing is that in the Markovian noise settings, we cannot use a step size where the gamma k decays slower than 1 over square root k.
Small question. Do we know that under these conditions, the solution to Poisson equations are unique? I guess you know, right? Because
it is unique because of the whoisness assumption.
Yeah.
So because of this assumption, so the solution will be unique because those eigenvalues will be strictly negative under the Howitz assumption. All right. So so the result for the Markovian case, I don't think I need too much explanation because it looks 99% similar to the Martingale case. So the only difference is that the transient term no longer only depends on the initialization, and there will be an additional constant that you have to kill using the exponential decaying term. And those actually depends on, for example, the mixing times of the Markov chains and also the upper bound on the matrix valued functions. So these are the two main results that we proved in that we showed in this paper. So far, any question for this? Okay, I think I will move on. So let me try to go through some of the high level of the proof idea. So there's a notational questions about the inequality tilde. So it simply means that we are hiding the constants in the inequalities. So we're hiding some constants.
It's a universal constant, I guess.
Yeah, some universal constants. Yeah. Okay, so some high level idea of how we proved it. So now let's recall that this is our linear TTSA iterations. So I have this theta k plus 1 and wk plus 1 updated in this way. So at the first site, analyzing this can be challenging because you see that once you update theta, you also update once the update for theta depends on wk, and then the update for w depends on theta. So they are coupled with each other. So one idea is that you try to design a single potential function that tries to tries to compute what is the optimality gap for theta, and linearly adding this to wk. So in this way, you have a single potential functions, and then you try to find, hey, let's say I start with I try to see what is the how large is j theta k plus 1 wk plus 1, and is it going to decrease? Is it going to be smaller than j theta k wk plus 1 wk? And then you try to, by bounding this progress, you try to derive a corresponding convergence rate of it. So the reason is that it doesn't allow you to exploit the two-timescale structure in a nice way. So the fix or the idea that we're going to use was actually taken from a more careful read of Condon and Cyclis. So they actually propose an idea that you can apply a change of variables and trying to decouple the updates into an equivalent formulations, and that is much easier to analyze. And as I show here, so we're gonna denote something new we call theta tilde, which is essentially the optimality of theta k and theta star. And I define another term called wk tilde. So this time it is a little bit different from. It is a little bit more complicated than theta k tilde, whereas it depends not only on wk minus w star, but it also depends on ck times theta tilde. So by using, and this ck is actually time varying terms, and by designing this ck carefully, we can show that the TTSA updates are equivalent to the following two equations. And what is important is that now if you focus on wk tilde, it does not depend on theta anymore. So what that means is that it is not decoupled from that of theta case. And the important implication here is that now I can try to bound WK in one by one. So just like I try to peel an onion, like I try to tackle the easiest one first, and then I try to look at how is the coupling between this and theta, how is it going to look like. So this brings us to this sketch of the proof. So for the starter, let's focus on the martingale case only. So for the martingale case only, as I said, we're going to start with W tilde first. So then with W tilde, it is going to be so for WK tilde, we're going to start by we're going to show that this mean square error, or actually the norm of the covariance, the norm of the covariance is going to follow this inequality. So once again, you have some transient terms and yada yada, but the important term here is the steady state term here, which involves the gamma k plus 1. The way we do is actually pretty simple in this way, because what we do is essentially I try to, based on the iterations I compute for W tilde k plus 1, I simply expand everything, and then I use the assumption that the noise is a martingale, so that I can eliminate a lot of the cross terms, and then I get a very nice and simple equation like this one. And I'm going to use assumption 4 about the noise variances, and those will give me this guy at the in the end of this equation. So, but the important highlight is that because of the decoupling tricks that we applied, where we decouple W tilde from the others, I am able to directly evaluate this. I'm able to evaluate directly these iterations and trying to compute the update form here. So this is how we did for W tilde. So what we're going to do as well is that we also want to focus on the cross term. We want to analyze also the cross covariance. That is the covariance between theta and W. We want to analyze this term. So this is the result. So the result here is interesting in the sense that the steady state term here actually depends on beta k, and as you recall, we have the other way around. And as you recall, beta k divided by gamma k is going to 0. So it means that the steady state here is going to be smaller than W. So this is nice. This is nice because this is going to be smaller. But I just want to warn you that as a caution here, because this is an important step. Because one way to get around with this cross term is that you may want to apply Cauchy-Schwarz inequality just to split the cross covariance into the covariance of theta and W individually. But this is going to result in the suboptimal weight because it is going to be gamma k from the first step. So now let's go through and then the last step for the onion peeling tells us that theta k also has this beta k steady state error. So now that after this onion peeling exercises, what we have here is that I have 3 inequalities, and I can actually solve and then here I want to solve for an unknown, which is the m theta, the mj theta, and basically by solving these recursive inequalities, we get a desirable result saying that this is going to be how my theta k behaves. So, I mean, just to summarize, I think the important step here is that we really need to exploit the cross covariance, and by exploiting that and showing that it has it enjoys the fast convergence with beta k, we can show the fast convergence for theta as well. And that is the main idea involved in the proof. So let me also quickly go through what we did for the Markovian case. So let us recall that the noise terms are generated by these equations. So by using the Poisson equations that was implied by our assumptions, we can actually do an add and subtract by adding PBXK and PBXK. And I can decompose the noise term here into one that is actually a martingale, and then a finite difference. And then the idea is that now I can apply the same tricks to all my A tilde and B tildes, and then I can split the noise terms as a martingale and also a finite difference. And I'm going to name this VK0 and VK1. And now let's also do the same splitting for the linear TTSA updates. So I have one iterations for theta tilde that is driven by the martingale noise, and one that is driven by the finite difference noise. And you can show that once you combine this together, it gives you the original error term that you want to compute. And you can analyze them separately as follows and you can show that essentially this martingale-driven noise will be much larger than the finite difference-driven noise. Because for one example is that if you focus on the first step for W, so since W0 is now like a martingale noise-driven terms, you can apply pretty much the same analysis as before, and you find out that there's a steady state error at the order of gamma. But then for the finite difference error, we find that the steady state error decays in the order of gamma square. So this one is much smaller than the other one. And then using this intuition, you can show that also the finite difference-driven error for theta is also small, and then basically you repeat the previous analysis to find the desirable error.
So can you explain shortly why you have gamma squared here?
The reason is that if I look at the finite difference noise, this noise here actually is actually very interesting because it obeys the order that there's a. So you're basically taking a sequence and you take the K sequence and subtract away the K+1 sequence, and then when we analyze the noise terms of this guy, before we take norms, before we take expectations, you can have a lot of cancellations.
It's like a telescoping thing.
Yeah, so this is actually, I think this is actually similar to, I mean, it is related to a recent blog post from Francis Bach. So I think this is something called Bell summations or something also. I mean, I don't know the precise name for this. I only know that there's a finite difference and you can play a lot of tricks to analyze the fast convergence of it. So is there any question here? So this basically finishes the sketch of the proof. And
yeah, like still this finite difference. Somehow I expected that you will use geometric convergence of the Markov chain or something like that.
And the convergence, so the convergence of the Markov chain, so in this case is actually embedded in the solution to the Poisson equation. So
only there where you use it? It's only there where you use it? There is no other place in this analysis?
So So because this bi hat was actually defined as like a infinite sum of the Markov chain.
Right.
This b something something. So because this is like an infinite sum with the Markov kernel. So when you make the summations, so you will find out that this bi hat is also a bounded function, provided that b itself is bounded. But then the upper bound for this bi hat function is going to be in the order of something like 1 minus the mixing time of the Markov chain,
Right.
multiplied by the original bound of the function.
Okay.
So that is to say that these mixing time things are all actually embedded into this bi hat thing. So here we are simply taking out the dependence on the step size and the decaying step size.
Yeah, Xiaofeng added something in the chat that maybe a log D factor is going to appear somewhere because of the geometric mixing too.
Yes, there's a log. No, why there's a log term?
Because there's this
log term. Why there's
I don't know.
No, I don't think there's a log term, because if you sum a geometric sequence, the lambda k,
it's constant, yeah.
There's no log, right?
Yeah, it's just a constant, yeah.
Yeah. Actually, I don't remember we have a log term in our bands.
Right. No log terms. Okay.
So let me go through the last main result of this paper. So we are also interested in knowing how tight our bands are. So actually, we did the following. We tried to do an asymptotic expansion as follows. So let's go back to the martingale noise case. We assume zero mean noise and etc. etc. So we show that actually the mean square error can be written as the composition of two terms. One is called ik, the other one called jk. So this ik actually has a closed form solution. You have, as long as you have this delta, you have this step sizes, you have this noise covariance, you can compute this in your MATLAB, in your Python, in closed form. And furthermore, this ik term is going to be in the order of beta k. Lower bounded and upper bounded by beta k. So there's a residual term. The residual term follows this inequality. And precisely, the steady state error here is dependent on beta k, gamma k, something like this. So which means that it is going to be much smaller than beta k. So meaning that eventually, ik will dominate jk. And we're going to see that as we evaluate the mean square error, really the noise the optimality you're going to see in the steady state is behaving exactly like this ik. So I see that I overrun a little bit. So let me try to finish quickly. Okay, so we actually did one toy example numerically. We tried to see, okay, we just fix aij, bi, and try to simulate with IID noise. This is my ik, this wet dashed line, and the other term, and then the other fluctuating lines are the mean square error for theta under different step size settings for gamma k. So they all behave exactly like we predicted. And then also for wk, we also see the similar decays according to how large the exponents for gamma k is. Of course, it also works for Markovian samples. So here we took the simple Garnet problem. I mean, these settings, that settings, and you see that basically it matches the beta k bound for the theta error, for the theta optimality, and matches the gamma k bound for the wk optimality. So as a summary, so in this work, we tried to close a gap in terms of the finite time error bounds for linear TTSA, demonstrating that there is a separation of scales with theta k converging at beta k weights, something like 1 over k, and then WK converging at the rate of gamma k, dependent on how you chose the step size for the for the faster time scale. We try to relax some artificial constructions that are made in the prior works that was merely used to assume boundedness, and also show that the martingale bound is sort of optimal using an asymptotic expansion arguments. So some future work that we have been looking at different directions. So one of the expansions that we are looking at is we first of all try to get rid of the Poisson equation altogether. We try to use a nicer bond for the instead of the Poisson equations. So, but instead of doing 2-timescale, we went back to the 1-timescale stochastic approximations, and actually we show that even if you evaluate the higher order error moments, you can actually expand the noise or the noise into as many terms you like, depending on how accurate you want your analysis to be. And we can show a similar separation of scales of these error terms, and that will depend on how large the step size that will depend on the powers of the step sizes. We are also looking at the nonlinear versions of TTSA and trying to tackle some non-convex bi-level optimization problems, and trying to apply this to autocritic analysis as well. And of course, since I actually came from a control background, so I'm also interested in, okay, what if we do some distributed TTSA? And so with that, I would like to conclude my talk and take questions. Thanks.
All right, thank you.
Thanks.
Yeah, sorry for overwhelming.
No problem at all.
Sorry for overwhelming this.
So Xiaofeng, I know that he had a question that hasn't been answered. Xiaofeng, are you around?
Oh, yeah. So I got a question about the assumption on the fast timescale step size. In Kanda and the T-Cyclis paper, there seems to be no restriction on the order of the faster timescale step size, right?
There's no restrictions on it. Let me see. There's no restriction. I wouldn't say they have no restrictions. They have one about the they have something close to this one. Like if I can most likely be wrong. So they have something like 1 over beta k minus 1 over beta k plus 1 going to beta.
Okay.
So they have something. So if I remember it. So that will define. Yeah, just saying. Yeah.
Yeah, that will be similar to this alpha constraint, right?
Yeah, yeah. So
okay.
Yeah. Right.
Okay, thank you.
Thanks.
All right. No question.
May I ask a question?
Oh, yeah.
Yeah, go ahead. Hey.
Hello?
Yes, I can hear you.
Yeah, hi, this is Gogan here. If you don't mind, can you go back to your assumptions on the martingale, this Markovian noise?
The Markovian noise, okay. So this one?
Yeah.
Not this one. So you had like some norm of this thing is less than something, right? Like.
Let me see. Maybe this one, but this is not the assumption. So I mean, let me go through the slide and tell me when I have to stop.
Sure. Maybe you go back to the assumptions.
Okay.
Yeah, maybe it was the martingale difference case itself, not the Markovian case.
Maybe
the martingale case itself. Yeah. So this assumption 4,
yeah.
right?
Yes.
Oh, so you have a assumption on the norm of the expected value.
Yeah.
Okay. Yeah, I just wanted to know this. That's all.
Okay.
Thank you.
Thanks.
Right, there were some comments. Shem, do you want to make a comment?
Sure. So this is great, but in normal stochastic optimization, 1/k type step sizes don't work well. So in this case, what do people usually do in practice? Do they use like a constant step size? Do they just do Adam again? And do we have an analysis for any of this?
So first
even
of
in
all,
the simple martingale case, I don't know.
Yeah. So first of all, for the constant step size case, our analysis does cover that. So basically, you can plug in the constant step size, and assumption 2 is automatically satisfied. So that is okay for constant step size.
Okay.
For Adam step size, I'm not sure if there's any successful application of it in the GTD settings, for instance.
I see. Okay.
Yeah, but maybe there are some. I'm not sure.
All right. Okay. Thank you.
Yeah. Thanks.
Yeah, I guess a follow-up to that is that, of course, if you have a constant step size, then there are other issues, right? Like you're not converging. Maybe eventually you want to make it small, but you can't because then that slows you down. Like if you do that too fast, and then the obvious idea would be to use averaging on the top. So
I think some people proposed that they can diminish the step size piecewisely.
Okay.
Yeah.
And is there an analysis for that?
I just remember that when we were writing this paper, I saw in one of the many references they used that.
Yeah, I was wondering whether there is a, and I guess maybe the ultimate question is always like how to make these recursions converge fast and in such a way that the step size choices don't depend on instance, right? So universal choices of step sizes somehow.
So maybe Adam is one, practical way.
Yeah.
You know.
So we see a comment from Xiaofeng that there is Adam for TD and gradient.
But for TD, it's not.
Xiaofeng, do you want to say what we know about this?
Actually, I don't know too much about the paper. I just know they done something about Adam for TD and policy gradient. Yeah.
I see.
Maybe. Okay.
Okay.
All right. So Mayank asked on slide 26 why the lower bound matches the upper post form.
26. Okay. Cool. Here. So the question is, why does the lower bound matches the upper bound in closed form? Oh, basically what we show is that there's a universal constant C1 and C2 that lower bounds and upper bounds IK in this inequality.
Yeah.
So then asymptotically IK will be lower bounded by some constant times beta K.
I guess the question is like, why do these inequalities hold? Like, do you have any like quick explanation of?
Oh, okay.
Expression and like somehow it seems that it simplifies beautifully.
Yeah. Currently we don't have a simplified slides for this. Basically, the proof idea is actually to expand everything. Yeah. So okay.
Just calculation.
Yeah.
Okay.
Thanks. I got that.
Yeah. So I see there's a question from Sergio, so maybe he can.
Sergio,
yes. Here you follow the Jacobi approach, right? Which other update k+1 based on k from the both variables. But Gauss-Seidel, in my experience, is typically much faster. Could the analysis extend to that case?
I see. That's a good question, but let me see how will it extend. Well, I don't have a concrete answer to this yet, but it seems that we. No. The question. I think there may be a problem if we want to extend this analysis. The reason is because of this observation. So so our analysis actually hinges on applying these Gaussian eliminations to simplify to decouple the updates. And if I try to update my parameters in a Gauss-Seidel fashions, I'm not sure whether maybe we have to develop different versions of this Gaussian elimination.
Yeah.
That should work. I think there is a paper, I don't remember. I mean, the last author is Golub, the one from Matrix Computation. And I remember they transform Gauss-Seidel in a kind of Jacobi form, and they analyze that data. Maybe
analysis. Yeah.
Yeah, thanks.
This is an excellent question.
Right. So there were some questions about the influence of the mixing time, and maybe can you explain how that shows up? Because you explained that there's this infinite sum that goes into the solution of the Poisson equations, but then so I guess you assume that the Poisson equation has a bounded solution. Yes. And then the scale of that shows up in the bound.
Precisely.
But to what order?
And because if we assume that A tilde is bounded under A5, so then you assume that there is a mixing time for the Markov chain, and then A hat will also be bounded, and then the bound will be dependent on the mixing times of the Markov chain. And so essentially you will be bounding something like B hat will be upper bounded by 1 minus rho of B infinity. I mean TV, yeah, actually. TV, sorry.
Right, and then how does this show up in the eventual bound that you get?
In the eventual bound, let me see, where can I say it?
I guess it's benign, right? Like it's not like in an exponent of something.
Yeah, it's not in the exponent of something. It's, for example, it's going to show up here because remember that we're trying to bound the finite difference driven error. So then we are going, even though we can make a lot of cancellations with the finite difference, eventually we're still going to have to handle something that depends on this guy. And once you take the TV norm of it, boom, you get that thing.
Right. Yeah, gotcha.
So I guess this upper bound is going. I think this upper bound is going to appear universally here.
Right. I see. So basically, you don't explicitly assume geometric mixing, and it's not like you truncate this infinite sum at some point. So that's why you don't.
We didn't try to optimize that this dependence on the dimension. We didn't try to optimize this dependence on the mixing time or so.
Well, this is a nice technique.
Yeah. I mean, if we had time, it would be nicer to find a better dependence on the dimension.
Right. Well, I didn't quite catch what would you do if you didn't have the Poisson equations. I don't know. Is that like too difficult to explain, or?
Is yeah.
Well, yeah. I mean, you showed the composition of the error. Yeah, I guess that's as much as I can say in this time frame.
Yeah, that would be a bit too difficult to explain.
Right. Yeah, gotcha.
Right. You mentioned very quickly nonlinear extensions. I was wondering about like how far did you get along that way?
So on that thing, we actually we didn't manage to get the same fast convergence as we have here. So we only got some slower convergence, something like so if we assume the bilateral optimization problem is strongly converse, then we have something like 1 over k square root k convergence. So which is not that optimal, not that nice, but that is non-linear.
Mm-hmm. And
one of the challenges in that analysis was when the stochastic approximations are non-linear, we couldn't do tricks like this step. We couldn't do something like this.
The highlighted one.
Yeah, the highlight ones.
Mm-hmm.
So I cannot really express my updates in terms of a linear transformation of one another, and then for a lot of the couplings we have to use Cauchy-Schwarz inequality, which is which works, but always giving you a bad weight.
Okay.
Yeah, I think nonlinear things are just more complicated, right?
But
data expansion instead of Poisson equations on slide 19. What does it mean by data expansion here? So actually, the reason why we want to use the Poisson equation is that we want to extract the martingale difference parts in the noise term. So therefore, if you try to use something other than the Poisson equations, then it doesn't give you this Poisson, this martingale plus finite difference structure to exploit. And I'm not sure whether Taylor expansion will give you the right answer here.
Yeah, so that won't take this guy into account. Okay. Yeah, got that. Thanks.
Yeah, thanks. So I saw in the chat box there is so Gugan mentioned the work by Markovian and Pelletier, but I think that nonlinear function is not a truly nonlinear function in that paper, if I remember. So
so they assume that close to the solution point it has a quadratic decay.
Yeah.
Right.
So so which in this sense it's it's not that nonlinear. That's what I meant.
And if you don't mind, can you go back to that lower bound again? In that lower bound, I was a bit surprised because if the noise is 0, then the convergence should be exponentially fast. So, right?
If the noise is 0, let me see. If the noise is 0. So if the noise is completely 0, then the noise will be... I see. So, but you see that here, the IK actually depends on the noise covariance. Okay. So if the noise is 0, then there's no IK.
Yeah, so that's why I'm surprised that the trace of sigma will be 0. But then that doesn't seem to be correct.
No, it's
So you were saying that if the noise is 0, right, then sigma will be 0,
Yes.
and the entire
Yes.
IK just go away.
I think the tightness
Okay.
was for sigma positive. That's it. And for sigma equals 0, you didn't claim tightness.
Yeah, of course not. Yeah, because I mean, if sigma equals to 0, there will still be something that is called JK, but we can only upper bound JK here. We don't lower bound JK.
Okay.
Yeah. So I mean, of course, we should refine the statement that assuming that sigma is non-zero.
Sure. And the other thing was, I noticed that you also cover constant step sizes, right?
Yeah. Mm-hmm.
But if I remember correctly, for constant step sizes, one cannot guarantee convergence. I mean, one can only guarantee that you go to some neighborhood of the solutions and stay there.
Right. So if I assume a constant step size, beta k will the static.
Okay. Yeah. Makes sense. Yeah. Sorry. Yeah. Thank you.